Okay, part A says show that C only has one stationary point. Okay, find the coordinates of this point. So remember, for stationary points, we do dy dx. We look at the gradient function. So if we differentiate this, we get 3x squared plus 18x plus 27. Okay, so we say then, look, for the stationary point, okay, dy dx is equal to 0. Okay, so we always go through that process because at the stationary points, the tangent will be horizontal, whether it's a max or min or whatever. In this case, it'll be a point of inflection, as we'll see in a minute now. But the tangent will be flat, so dy dx is 0. So we'll put the gradient function there equal to 0, and then we'll solve it. Now, before we factorise this, look if there's any common factors, and it is. 3 goes into it, so if we divide by 3, we'll have x squared plus 6x plus 9 equals 0. So then, two brackets here, two numbers that multiply to give 9, add up to give 6, well, they'd both be positive 3, won't they? Okay, so they're both going to be the same. 3 times 3 is 9, and positive 3 and positive 3 is plus 6. So therefore, if you notice, we've only got one set of results, really, haven't we? Because x plus 3 is 0, or x plus 3 is 0, just means then x is minus 3. That's all you're going to get. So it says show that C is only one stationary point. Well, we've done that, haven't we? We've shown it through this process. Just one answer. We need to find the coordinates, it says, of this point, yeah? So when x is minus 3, we'll work out what y is. So you've got to sub it in there, yeah? Like this. So use your calculator. Okay, that's right there. So that comes out to be 4. Okay, so one stationary point at minus 3, 4. Okay, so then your part B, then it says verify that this stationary point is a point of inflection. Okay, so a point of inflection is different to a maximum or minimum, because what happens is with a maximum, if you think about a maximum sort of rises, it hits its max and then falls again, whereas with a minimum it falls and then hits its minimum and then rises again. With a point of inflection, okay, it rises, becomes flat, and then rises again. Okay, so it's rise, flat, rise. Or it could be the other way around. It could be falls, becomes flat, and then falls again. Okay, so what we need to do is, okay, suppose it's this situation, it doesn't matter which situation it is, that's where my stationary point is, there, okay, that's where the point of inflection is going to be. We need to look at dy by dx either side of it. Okay, so if we look at dy by dx this side and that side, and if they're both positive, then we've shown as a point of inflection. Okay, which kind of differs, doesn't it, from when it's like a maximum? Because when it's a maximum, if you look at dy dx before it is positive, after it it's negative, and the same here. If you look at a minimum, dy dx before it is negative, dy by dx after it is positive. So point of inflection, it would be the same before and after. In this case, it's positive, positive. In the case here, before it would be negative, and after it would be negative. Okay, so that's how we go about it. Now you might be wondering, why don't you use d2y by dx squared like we normally do? Well, watch what happens when I do use d2y by dx squared. Okay, d2y by dx squared in this case. Okay, well, if you differentiate that there, you get 6x plus 18. So when x is equal to minus 3, d2y by dx squared is equal to 6 times minus 3 plus 18. I'll notice it comes out to be 0. So if it's 0, it's not positive, it's not negative. So you can't say it's a max or a min. Okay. Having said that, even though it's equal to 0, okay, we can't be certain that it's a point of inflection. It could still be a max or a min, right? We're in that sort of situation where we're not sure. Okay. So what we'll say here is when it's equal to 0, we say implies it could, right? It could be a point of inflection. So it's important to mention that. Okay, it could be a point of inflection. So let's prove this point of inflection. Let's have a look at what the gradient is either side of this stationary point. So remember, the stationary point occurs at minus 3, 4. So what I'm going to do is I'm going to look at dy dx either side of minus 3, 4. So if you think of a number line, minus 3 is there. Either side, well, that point there will be minus 4, and this point here will be minus 2. So let's look at what the gradient is when x is equal to minus 4 then, to the left side of this stationary point. Dy by dx will equal to, so we'll sub it in, 3 times minus 4 all squared plus 18 times minus 4 plus 27. So I work that out. That comes out to be 3, which is positive. When x then, let's go the other side, is minus 2. Dy by dx is equal to, so we work that out. That also comes out to be 3. So notice the gradient is the same on both sides of the stationary point. So another way of illustrating it as well is where the stationary point, the tangent would be flat, wouldn't it? Okay, so in other words, when x is equal to minus 3, the tangent would be flat. But when x is equal to minus 4, the tangent is positive. And when x is equal to minus 2, the other side of it, the tangent is also positive. So you can see there the point of inflection. So part C then, it just says to sketch the stationary point. So quite simply then, at this point of minus 3, 4, okay, so minus 3 would be here, 4 would be here. Okay, so it's going to be literally like that, okay? So you can see there your point of inflection is there, okay? So it rises flat. Just try and get this as flat as you possibly there at that point, and then rises again.